Harsh lighting can detract from the quality of a photo. Here's one taken on a sunny day. Notice the strong shadows and specular reflections, as well as the distracting contrast between the lit and shadowed areas. Professional photographers can address this by setting up scrims to diffuse the light. This requires custom hardware, along with time and expertise on the part of the photographer. The result, however, is visually pleasing, with softer shadows and specular reflections. We would like to provide this diffusion effect to users without requiring any specialized equipment or expertise. We propose a method that takes just the image of a subject under uncontrolled lighting and enables controllably diffusing the effect the lighting has on the subject. Furthermore, we propose an extension of our light diffusion technique to predict the albedo image of the subject. Using our new albedo prediction method can aid in improving tasks like totally replacing the lighting environment of the subject. To generate our ground truth data, we record subjects inside of a light stage, producing one light at a time images. Using these one light at a time images, we can visualize the subject under an arbitrary HDR environment map. Crucially for our use case, we blur this HDR environment map with a normalized clamped cosine kernel, which diffuses the light inside the scene. The power of the kernel controls how diffused the resulting HDR map will be. In addition, we construct a shadow map that represents how much darker the source image is relative to the image we get after diffusely blurring the environment map. Similarly, the specular map represents areas where the source is brighter than the diffusely lit image. Because the light stage is a very controlled environment, we cannot produce images with external shadows. To bridge the gap to real images, we augment the data by synthetically casting shadows onto subjects, projecting textures onto a 3D representation of the subject, softened to agree with the diffuseness of the incident lighting. Using all of this data, we train an image-to-image system to perform light diffusion on unseen subjects. We start with just the source image and an automatically extracted alpha matte for the foreground subject. The first model in our system estimates the single-channel brightening and darkening lighting maps. We concatenate these maps with the input images, along with the parameter indicating the desired amount of light diffusion, and feed everything to our second stage model. The output of this stage is the foreground with partially diffused lighting. Lastly, we use the original alpha matte and the estimated foreground to compose it back into the original background. To extend our framework into albedo estimation, we train a version of our model specifically to always estimate the most diffuse version of the output, that is, blurred with the simple cosine kernel with exponent 1. We then apply this model several times recursively. This repeated diffusion has the effect of simulating illumination with a constant environment, tinted by the average color of the environment. To account for the tint, we take a face crop of the subject and train a small model to estimate the color of the tint. Once we know the tinting color, we can simply divide the tinted albedo by the color value and obtain the untinted albedo image. Our portrait albedo estimation extension shows promising results. Here we compare our albedo estimation approach to several other state-of-the-art methods. Albedo variation on clothing and the influence of shadows can be particularly difficult to handle. Our method outperforms the others in these difficult cases. Failures in albedo estimation are the largest sources of problems in state-of-the-art relighting methods. Using our improved albedo estimation, we demonstrate improvements in the downstream total relighting task of Panday et al. Note the improvement in clothing color consistency and removing leftover shadow edges. Our shadow augmentation allows us to effectively deal with shadowing, and when we evaluate at full diffusion, we show favorable results when compared to the method of Zhang et al. On portrait shadow manipulation. Note that even though portrait shadow manipulation often lightens the shadow, it leaves noticeable traces of the original shadows. Additionally, by effectively attenuating difficult shadows in specular regions, we can also improve other downstream tasks, such as face parsing. Here we operate on the fully diffuse images and show significant improvements in segmenting regions of the face. We now show a variety of results applying our parametric diffusion model. Notice how the image changes with different settings of the diffusion parameter. Our model manages to naturally diffuse shadows and diminish effects of specular reflections. For an appealing look, we vary the parameter within a range that avoids fully diffusing the lighting, which usually looks unnatural, inconsistent with the rest of the scene. Finally, while our model wasn't trained with video applications in mind, we can apply our technique to videos with unpleasant lighting. We apply the model frame by frame, improving the visual clarity of the subject. Note that the method appears to be temporally stable even without enforcing any temporal coherence. For further results, please refer to our supplementary materials.